Welcome to class. Today we're going to talk about some eruption products from volcanoes. Last time we talked about how they were made and the different types of magma and where they're formed. Today we're going to talk about what comes out of them. And then we're going to talk a little bit about mountains. So first, what are some warning signs that you're going to get before a volcanic eruption? So take a moment, think about this, scribble a couple down. Now you may have guessed that since these are caused by tectonic activity, a lot of the stuff we're looking at is, we're going to be covering more frequent earthquakes, change in shapes as this magma starts building up and piling up. You can get bulges on the land. And then another big one, if you see a lot of volcanic gas around here, it's a good idea something's cooking. So this is a picture in your book. I would recommend looking at it. It's kind of a Cliff's Notes version of all the fun stuff. We're just going to talk about fun, by the way, was in air quotes. None of this is really fun, because it's burning magma. But we're going to go through. This is a Cliff's Notes. The picture's in your book. Please take a look at it. Two types, or classifications we're going to look at: airborne and whatever flows on land. So here's Mount St. Helens. This eruption happened in 1980. This is pre-eruption, by the way. See the tree line, see the little thing. And then, Mount St. Helens erupted. Now, where was Mount St. Helens? It's on the coast of Washington, so you can think, alright, convergent sea, oceanic plate going under, probably andesitic magma, so it's kind of in that middle range. When it blew, it knocked off 400 meters, 1,300 feet off the top of its elevation, and all those trees that were there, just gone, just taken out from the side. So the reason they were taken out from the side is this idea called lateral blasts. Most of the time things blow up. That being said, when sometimes pressure gives on the side, and they just pop out the side. And a lateral blast just took out all the trees on the side of that mountain. Pretty impressive. Up to 12 kilometers away, it just nothing. And then 25 kilometers distant, you can knock down trees. So it's a pretty important product. When volcanoes go, they go, well, depending on the type. But when an andesitic volcano goes, viscous lava, hard for bubbles to escape, and violent eruption. Here, tephra. Tephra is just any particle that gets shot out the top of a volcano. Then there are these particles called volcanic bombs. Volcanic bomb is this magma that goes up, then it hardens as it cools in the air, and then it comes down as rock. So it goes up liquid, cools, hardens, and then just falls down as rock. It can be pretty big. And then volcanic ash, which coats Pompeii. So volcanic ash, this is an example I like, kind of close to us. It's near Creighton, and that dot needs to be closer, actually up here. Sorry about that. Needs to be right up here. Near Creighton. These are fossilized rhinos from 12 million years ago. From a volcano in Idaho. So this was a giant volcano in Idaho that exploded. The ash was carried up to about 1,600 kilometers away and deposited, and now you have fossilized rhinos in Nebraska because of a volcano in Idaho. These products go fast, and they can linger for months or even years. One of the eruptions they were talking about, there's 1816, I believe, is called A Year Without Summer, because volcanoes erupted, blotted out some of the sunlight, and then just produced a massive cooling feature on the Earth. Tephra facts. You're not going to be tested on those, but go back and look at them. Volcanic gases. These are another big things that may affect climate patterns. Sulfur dioxide blocks insolation temporarily up to a year, reducing global temperatures. This is just what we talked about. Sulfur dioxide also kind of smells like rotten eggs, so not so great. Now, volcanoes produce a ton of carbon dioxide. But it's still only 1% of the carbon dioxide produced by humans in our products. So, not big comparably, but it is a pretty big source. This rate, if we track through history 120 million years ago, that's what this big mega million years ago, there was enough carbon dioxide from volcanic eruptions to raise the temperature of the Earth. Now let's go and see what happens on land. So first, low viscosity lava, 50 kilometers from the source. This would be your, low viscosity, high or low silica content. Low silica, Low viscosity, it's going to flow. All right. Remember, silica looks like little tendrils, like spaghetti. Hard to get it going. Low silica flows. Now, normally, this goes about 1 kilometer an hour when it's out in the open, but if it gets in a lava tube, it's kind of like a stream bed for lava, it can go up to 30 kilometers an hour, which is reasonably quick. But it just goes and it just keeps building and building and building. Higher viscosity lava normally remains within the volcano crater. It's thicker, it bubbles up, it doesn't flow as far as fast, so it just kind of pops up. And you get these lava domes, which are just big peels and big hills, kind of on top of a crater. Pyroclastic flow is also something that kind of goes down. It's this disk cloud formed by a combination of tephra and volcanic gases. Just a big cloud of yuck, fast moving 100 kilometers an hour, that's 60 miles an hour, down the hill, and it's 700 degrees Celsius. So it's this big hot moving flow that just goes and kind of vaporizes whatever's in its path. And then layar, from an Indonesian word for mud flow. So what happens in a layar is that volcanic ash, mud, volcanic debris mixes with streams or ice melt, and then it flows this, well, pretty much like a mud slide down stream beds and just takes out a whole bunch. This is a little person kind of sitting there. Very destructive, often confined to stream channels, so it's predictable, you know where it is, but you don't want to be in its way. Now, one of the things that I want you to remember, and probably worth going back and taking a look, is look at how all of these products interact with other things. The stuff gets thrown up in the air. Oh, now you're interacting with the atmosphere. Layers, now you're interacting with the hydrosphere. All of the oceans, the atmosphere, water, Earth, the geosphere, lithosphere that we're talking about, all of that mixes together. And that's going to be the hallmark of this class. We're going to go through and see how every system affects another one of Earth's systems. Let's talk a little bit more volcanoes. There's 3 types: shield, stratovolcanoes, and cinder cone. They're all made of different materials. You guessed it, different type of magma. And their volcano type and eruption style varies with plate setting. Now that just means, oh look, subduction zone. Are we going to get low silica, high silica? So it's another way of saying it all is dependent upon the composition of flow, just like how violent the eruptions are. So we're looking at a shield volcano. Shield volcanoes are wide and low. They look like a Roman shield. Mild eruptions, so if they're mild eruptions, they're low viscosity basalt, or basalt flows, like the Hawaiian Islands. It goes, it flows out wide, and then it just keeps stacking and stacking and stacking. Associated with divergent boundaries, which is where you find your low viscosity magma. Okay, so they're just gentle slopes. They go, it flows fast, and then it spreads out wide. This makes the tallest mountain, well, almost the tallest. It's about 28,000 feet is how tall the Hawaiian mountain would be, Hawaiian volcano would be, if you measured from the seafloor. But we measure from where the sea starts, so we don't think it's that tall. Stratovolcanoes. Any picture you see of kind of an imposing volcano on most of the time, stratovolcanoes. These are andesitic magma, so higher viscosity, medium viscosity overall. Real light's the real heavy one. So medium viscosity, oh, it's not going to flow as far. So what we get are these kind of steeper sides, mostly at convergent plate boundaries. And this is the most common volcano type. The Ring of Fire, the Andes Mountains, all the stuff you'll see around the Alaskan coast are this type. Cinder cones are very small, very viscous, coarse magma. When they blow up a lot. Right? So they may actually form on the slopes of shield or stratocone volcanoes, just because you get a pile up of stuff and then it just erupts. It just goes. This is the most violent eruption you're not ever going to see, but it's the most violent eruption of the volcano types. And again, that's because it's rhyolite, hard to get the bubbles out, but when it does, it gets them out very well. Here's some other fun features. Now, keep in mind, you have a project coming up where you can use national parks or finding how these systems interact with one another. So let's talk about it. This is a picture of Crater Lake out in Oregon. Crater Lake is actually a caldera, and a caldera happens when the magma chamber on a volcano collapses in on itself. So it just filled with water over the years and made this nice lake. Now, this is the Old Man in the Lake. It is a 9-meter, that's about a 30-foot tall tree stump that just floats vertically in the lake. Since for the past over 100 years, it just floats around. That's it. I thought it was neat. And so now if you go to Crater Lake, you can go and see him. Still there, floating. Okay, lava plateaus. Lava plateaus are just these big basalt. Remember, basalt is low viscosity, so they just spread out, and it just goes everywhere, and they make these little flat patches. Now, the cool thing about this is if we look at the map, these track to some of the biggest volcanic eruptions in history. All right, and there's just this big flat. So if we look at these are from the 120 to 80 million years ago, and they produce the hothouse conditions. Other fun features, which you can all find in Yellowstone, another national park you could look at, where you have these water reserves sitting on top of some magma. This hot magma gets hot, and if it gets hot and pressurizes, forces that water up little fissures and channels, and you get a geyser. If it doesn't, if you just heat the water, you can get a hot spring. It's got a nice little bubbling brook to go to. Consequently, most hot springs smell kind of like sulfur. Oh well, at least they're warm. Other fun things. You have acidic water mixing with weird chemicals. Not weird, they're in the earth, they're not really that weird. And it makes this mud, goopy, clay-like substance that just kind of plops up. It's like blub, 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 blub in there. It's pretty neat. So that's a mud volcano. And then fumaroles. No volcanic gas, or no volcanic gases. They're all volcanic gases. There's no water. And it just spits up just big carbon dioxide, sulfur dioxide, big steam. Now, none of these things will actually produce magma, but they're the result of being close to a magma pocket. And to wrap up with, let's talk about mountains. So we're going to switch gears a little bit and talk about what actually makes a mountain. So what you need to know, it's convergent or divergent boundaries. Convergent, good. If they're higher boundaries, higher younger mountains are long convergent boundaries. Lower older mountain belts represent old ones. So why would the higher mountains be youngest? Time hasn't taken its toll on them. They haven't eroded, which we'll cover in Chapter 9. Where are they? If we look at the highest mountains, these are active plates right here. And you'll notice they are all on convergent boundaries. Appalachians, depending on how you want to say it, but the Appalachian Mountains, they're lower, more rounded. It's an older convergent zone. So when you make a mountain, well, look at the Himalayas. They're the biggest ones we have. So India starts coming and crushing up against Eurasia. Now look, keeps on going, keeps on piling this up. So what type of fault do you get at a convergent continent-continent collision? Okay, so it's a reverse fault. And you see, you've got this little narrow thing, you push in, this part's going to go vertically, and as it keeps stacking, you make taller and taller mountains. But this isn't the only thing that affects mountain height, and we'll discuss that in a little bit. So until next time, I will see you later. See you in class on Wednesday. Hope all is going well. Thanks. Bye.